Imagine for a moment the hidden engines that power our entire digital world. Those tiny microchips, they're in everything, right?
Right.
Your smart thermostat, the servers running cutting-edge AI. But what if the very blueprint for these chips, the fundamental language they speak, was undergoing this quiet yet pretty profound revolution right beneath our noses?
Yeah, that revolution is undeniably centered around something called RISC V. It's an open standard instruction set architecture, or ISI. You can think of an ISI as the sort of contract between the hardware and the software. It defines the core commands a processor understands.
Okay.
And the really game-changing part about RISC V, it's completely royalty-free and open. That means anyone can use it, modify it, innovate on it, without paying a dime in licensing fees.
Right. So our mission today in this deep dive is to peel back the layers and discover why RISC V isn't just another tech trend. It feels like more than that.
Oh, absolutely. It's genuinely a paradigm shift. I mean, it's evolved from this niche academic project into, well, a geostrategic asset, really. It's reshaping how we build computers, unleashing a whole torrent of innovation, and, yeah, sending ripples across global geopolitics.
So you're about to uncover why major tech companies are pouring resources into it and how it impacts, well, everything from the tiniest sensor to the most powerful AI systems.
And if you consider the broader implications, this isn't just about making chips simpler to build, although that's part of it. It's about radically shortening the innovation cycle.
How so?
Well, imagine a world where the speed of technological advancement isn't bottlenecked by, proprietary complexity, but actually accelerated by an open standard.
Yeah.
That's the true democratization of chip design we're starting to witness.
Okay, democratization of chip design. I like that. So where did this whole concept, this open ISA idea actually begin? What was the spark?
It started, perhaps surprisingly, as a really concise 3-month academic project. Back at UC Berkeley, May 2010.
3 months. Wow.
Yeah. Professor Krista Jasnovich, along with David Patterson, who, by the way, was a pioneer of the original Berkeley RISC projects back in the 80s, so real history there.
Right.
And students Andrew Waterman and Yunsuf Lee, they had this very clear vision. They wanted to create a clean slate ISA, one completely unburdened by all the legacy complexity, the restrictive NDAs, the steep costs of existing proprietary ISAs like ARM and by ED6.
So they were basically tired of trying to build, new skyscrapers on crumbling old foundations. They just wanted a fresh start.
Precisely. That's a great analogy. They found those existing ISAs were just too cumbersome, too expensive, really, for academic research, and even just for teaching. So this clean slate approach let them prioritize technical merit, simplicity, modularity, right from the ground up.
And then the name RISC V, pronounced RISC V, that carries a bit of history too, doesn't it?
It absolutely does. It signifies the 5th generation of reduced instruction set computer, or RISC, research from Berkeley. It builds on those influential RISC and RISC-2 projects from the early 1980s. And when you look at its core design philosophy, simplicity, modularity, extensibility, it's not just talk. What's genuinely remarkable is the sheer difference in the documentation. The RISC-V spec manual, just 236 pages.
Wow.
Compare that to like over 2,000 pages for ARM32 or by 8632. That simplicity, it translates directly to smaller, more efficient, lower-powered chips.
Right.
It's like having a concise quick start guide versus, a multi-volume encyclopedia.
I can imagine designers getting pretty excited about that. Now, it started in academia, but how did it transition into something with, global impact?
Yeah, the crucial step was establishing the nonprofit RISC V Foundation back in 2015. This was vital because it ensured no single company or entity would control the ISA. It maintained that open nature, built trust.
Makes sense.
Then, in what turned out to be a brilliant strategic move, they relocated RISC V International's headquarters to Switzerland in 2020.
Switzerland. Why that?
Well, it was explicitly done to maintain geopolitical neutrality, to insulate it from trade disputes, export controls. That's absolutely vital for fostering global trust, especially for companies and, frankly, nations looking to invest in a long-term technology roadmap.
That makes a lot of sense. Now, one common misconception, I think, is the difference between an open standard and open source. Can you clarify that for us? Because they sound similar.
Yeah, it's a really important distinction, and it gets confused often. RISC V isn't open source in quite the same way, say, the Linux operating system is open source.
Okay.
Instead, maybe think of it using the analogy of Ethernet or Wi-Fi or USB. The specification for Ethernet is an open standard, right? It's free for anyone to use to build a network card. But the actual hardware implementation inside that card, the chip itself, That can be proprietary.
Ah, okay. So the recipe is open, but my actual cake can be my secret family recipe or maybe something I share. It's up to me.
Exactly. That's a perfect way to put it. This model, it decouples hardware innovation from software compatibility.
Right.
And what that means for you, the designer, is dramatically reduced software development costs because software can be reused across all sorts of diverse hardware implementations. It truly democratizes chip design by removing those huge financial and legal barriers that come with proprietary ISAs.
We've talked about its simplicity and openness on paper, but how does that translate into the actual architecture? Like, what does it look like when you peel back the layers of a RISC V chip?
Okay, so every RISC V processor starts with a base integer instruction set. Think of it as the fundamental building block. For example, you've got RV32I for 32-bit systems or RV64I for 64-bit systems.
Right.
And for really tiny, cost-sensitive microcontrollers, there's even a specialized RV32E variant. It actually reduces the number of registers just to cut down on silicon area, save cost.
Makes sense.
And a key design principle here is regular instruction encoding. All the base instructions are a fixed 32-bit length, which greatly simplifies the hardware logic needed for decoding them. It makes the hardware simpler.
Okay, simpler hardware. But you mentioned this modularity. This is where RISC V truly flexes its muscles, right? The power of extensions. How does that work in practice?
Yeah, it's like building with advanced Legos, in a way.
Yeah.
Designers can precisely tailor a chip's feature set for specific needs by adding optional standard extensions.
So like optional extras.
Exactly. One of the absolute cornerstones, especially for embedded systems, is the C, or compressed, extension. This is critical because it uses 16-bit encodings for common instructions. That significantly improves code density.
Meaning smaller code size.
Yes, exactly, which means you need less memory. And this can actually be on par with, or sometimes even slightly better than, ARM's Thumb 2 compression. That directly addresses cost and memory footprint, making RISC V incredibly competitive in that embedded space.
And for the cutting edge stuff like AI and high performance computing, you mentioned the V, or vector extension. You said that sounds like a game changer.
It genuinely is. I mean, think about the nightmare AI developers face today, right?
Yeah.
Constantly rewriting, optimizing their code for every new piece of AI hardware that comes out.
Yeah, sounds exhausting.
RISC V's V extension, with its vector length agnostic design, it kind of eliminates that headache entirely.
Yeah.
You write your AI algorithms once, and they basically scale automatically across everything from a tiny sensor doing edge AI to a massive supercomputer. No recompilation needed.
Wait, really? The same code runs everywhere?
The same compiled binary, yeah. The hardware tells the software how long its vectors are. It's an unparalleled accelerator for AI innovation because it removes that software porting burden.
That is a huge benefit. So beyond compression and vectors, what other capabilities can designers build into these RISC V chips?
Oh, there's a whole comprehensive suite of other ratified extensions. These allow for everything from, standard math operations like multiplication, division, the M extension, floating point calculations, F and D extensions, to handling multiple cores efficiently using atomics, the A extension, and even secure virtualization with the H extension for hypervisors.
Wow, okay.
There are extensions for bit manipulation, B, cryptography, ZK. The idea is to provide all the standard tools, whether you're building a tiny low-power embedded system or a high-performance data center processor. They call the common baseline G for general purpose.
And the customization, you mentioned adding unique instructions.
Yes, and this is really powerful. Designers can add their own unique non-standard instructions to accelerate highly specific workloads. Maybe custom AI functions, digital signal processing, specific crypto algorithms, all without breaking the standard software tool chains. That's a huge advantage.
That level of customization sounds incredible, but what about security? In this open world, how does RISC V ensure system integrity?
Right, security is obviously critical. RISC V incorporates robust security through privilege levels, similar to what you'd find in other modern architectures like ARM or x86.
Okay, the different modes.
Exactly. You have machine mode, or M mode, which is the highest privilege level, usually for firmware, then supervisor mode, S mode, typically for operating system kernels like Linux. And finally, user mode, U mode, where your applications run.
Standard stuff.
Very standard, yes. But crucially, they've also included the Physical Memory Protection Unit, the PMP. This is really important. It allows M mode, that highest privilege level, to define and protect up to 64 different memory regions, basically preventing unauthorized access from lower privilege levels.
Ah, so you can wall off sensitive areas.
Precisely. It's vital for creating secure enclaves, sometimes called trusted execution environments, and ensuring critical data, like cryptographic keys, can't be compromised, even if, say, the OS kernel or an application gets attacked.
Okay, that makes sense. Now, for any technology standard to truly succeed, it needs more than just a good spec, right? It needs a robust, vibrant ecosystem. How is RISC V building that global powerhouse around its open standard?
Yeah, the ecosystem is absolutely key, and the role of RISC V International itself is paramount here. As we mentioned, it's a global nonprofit acting as that neutral arbiter. It owns and maintains the specifications, ensuring they remain permanently open and royalty-free. This foundational trust, especially with its geopolitical neutrality based in Switzerland, is just fundamental to its global adoption.
The natural question for many, though, is always about the software. We touched on it, but is the software stack really mature enough? Can it actually support this revolution? Or is it still a bit of a Wild West for developers?
That's a very valid concern, and honestly, it was a bigger issue a few years ago, but it's being addressed head-on with incredible speed now.
Okay.
For core tools, RISC V is fully supported by the major open-source compiler toolchains, GCC and LLVM Clang. That's table stakes, really.
Right, you need those.
Absolutely. For operating systems, it hit a crucial milestone with mainline Linux kernel support, starting around version 5.17, plus official ports for major distributions like Debian and Fedora are available. For the deeply embedded world, Zephyr and FreeTOS have mature support.
And the big one, Android.
Yes. What's particularly significant, especially for you, the consumer potentially, is that Google has announced official support for RISC V in the Android open source project, AOSP. That really paves the way for future RISC V smartphones and tablets.
That is a huge vote of confidence, isn't it? Google getting behind it like that.
It absolutely is.
But does Google's backing completely de-risk it? Or are there still significant hurdles for RISC V adoption, even with such powerful allies?
Oh, Google's endorsement is definitely a massive accelerant. It signals serious commitment from a major player, no doubt. However, the ecosystem still needs to catch up in terms of, say, comprehensive software optimization and the sheer breadth of developer tooling that's been built up over decades for ARM and x86.
Right, that legacy matters.
It does. But the momentum is just undeniable. And on the hardware side, we're seeing a true explosion of implementations. It's not just software, the hardware is booming too.
Can you give us some examples of that hardware proliferation? Who's making these RISC V chips or cores?
Sure. We're seeing a really vibrant market for IP core providers. Pioneers like Sci-Fi, founded by the original RISC V creators from Berkeley, actually offer a wide range of cores.
Okay.
Other key players include Andes Technology, mostly focused on embedded, and Codasip, known for customization. And significantly, even the major EDA and IP vendors like Synopsys and Imagination Technologies have entered the market with their own RISC V core families. They see the writing on the wall.
So the big players are getting involved too.
Definitely. And beyond commercial IP, you have important open-source hardware designs like Berkeley's famous Rocket and Boom cores, which are great for research and as starting points. And then there's SRV, known as the world's smallest RISC V CPU. It demonstrates the architecture's extreme scalability and efficiency at the tiny end.
And for developers, hobbyists, can they get their hands on hardware easily?
Yes, increasingly so. Affordable development boards from companies like Sci-Fi with their Hi-5 series and Star5 with the Vision 5 boards are making RISC V hardware much more accessible to developers worldwide. You can buy them online pretty easily now.
Given this rapid development on both hardware and software, the critical question becomes, how is RISC V addressing that lingering software maturity gap in a really concerted industry-wide effort?
Right, because individual efforts only go so far. This is where the RISE project, that's RISE, the RISC V software ecosystem project, comes in. It's a truly global consortium.
Who's involved in RISE?
It's led by industry giants. We're talking Google, Intel, NVIDIA, Qualcomm, Samsung, Red Hat, a real who's who.
Wow, okay, so competitors are collaborating here.
They are. Their mission is basically to pool resources and accelerate the development of high-quality, performance-optimized open-source software, specifically for RISC V application processors, the kind you'd need for mobile, PCs, data centers. It's directly addressing that ecosystem maturity challenge by collectively building the foundational software needed for these higher-value markets. It's a significant collective investment in the future.
That sounds crucial. So what does this all mean for the market then? Is RISC V truly disrupting the existing, let's face it, duopoly of x86 and ARM?
It absolutely is, and at an astonishing pace, really. RSCV is no longer just some theoretical alternative on the horizon. Market adoption has really moved from a trickle to a flood.
Do we have numbers on that?
Yeah, by the end of 2022, Semico Research estimated over 10 billion chips containing RISC-V cores had already shipped. That's billion with a BIVA.
10 billion already.
And the forecasts are projecting compound annual growth rates, CGRs, of over 30%, maybe even 40% through 2030. Market sizes could potentially reach, depending on the analyst, anywhere from $7 billion to maybe $11.5 billion by then.
That's explosive growth. Why is this rapid adoption happening right now? What are the main driving forces?
It feels like several factors are converging. One is the slowing of Moore's law, which is pushing demand for specialized custom architectures because you can't just rely on general-purpose CPUs getting faster automatically.
Right, domain-specific architecture.
Yeah, exactly. Then there's companies' growing desire to reduce costs and, crucially, avoid vendor lock-in with proprietary solutions like ARM or x86. They want more control.
And the geopolitical angle.
And perhaps most crucially now, nations are making strategic pushes for technological sovereignty. They see RISC-V as a way to achieve that.
So let's compare directly. How does RISC-V really stack up against the decades-long dominance of x86 Intel and AMD and ARM? What are the key differences if you're a chip designer or a company choosing an architecture?
Okay, the business models are fundamentally different, first off. x86 is basically a vertically integrated duopoly, right? Intel and AMD design and sell their own chips.
Got it.
ARM licenses its proprietary IP. They charge significant fees up front, and then royalties per chip shipped.
The ARM tax, some call it.
Yeah, that's the term sometimes used. RISC-V, on the other hand, has no licensing fees, no royalty fees for the base ISA itself. Its ecosystem thrives by selling value-added products and services based on the open standard things like specialized IP cores, software tools, design services.
And architecturally.
Architecturally, x86 is a complex instruction set computer, CISC. It's burdened by decades of backward compatibility requirements, making it inherently complex. ARM is RISC, reduced instruction set, but it has also accumulated quite a bit of complexity over its lifetime. RISC-V, designed much later with hindsight, is arguably a purer, cleaner, more modular RISC design.
For a long time, though, the perception was that RISC-V was maybe good for embedded, but not for high performance. Is that outdated now? How does it truly fare in terms of performance, power, and area of the PPA metric?
That perception is definitely outdated. High-performance, out-of-order RISC-V cores are commercially available now from multiple vendors, and their performance is rapidly closing the gap with incumbents like ARM's Cortex-A series.
Really closing the gap.
Yes, and the key here is often its simplicity and modularity. This means RISC-V cores can frequently achieve comparable performance, but using smaller silicon area and consuming lower power. That PPA advantage makes them incredibly competitive, especially in power-constrained devices like wearables or IoT, but also where you want to pack more cores onto a chip, like in accelerators or servers.
And perhaps the most compelling evidence of market viability is seeing who's actually adopting it. Who are the major players making these strategic bets on RISC-V? You mentioned some.
It's an impressive and growing list. Many major players are adopting what you might call an inside-out strategy.
Inside out.
Meaning, RISC-V is first used for auxiliary, control, and embedded functions within their larger, more complex systems on chips, often alongside ARM or x86 cores. This creates a kind of low-risk, high-volume entry point for them to gain experience.
Can you give specific examples?
Sure. NVIDIA famously uses RISC-V cores for internal control functions within its GPUs and other complex chips. Meta is reportedly using it for control planes in their AML accelerators. Qualcomm is using RISC-V microcontrollers extensively in things like wearables, Snapdragon Wear, and automotive chips.
Qualcomm too, interesting.
Yeah. And perhaps one of the most significant signals recently is Infineon, a world leader in automotive microcontrollers. They're strategically pivoting away from their long-standing proprietary tri-core architecture towards RISC-V for new families of automotive MCUs. That's a massive shift.
Wow, that is big for automotive.
Huge. Then you have Alibaba's T-Head division in China, heavily investing in RISC-V for cloud and edge computing, partly for self-sufficiency reasons. Western Digital has shipped billions of RISC-V cores in its storage controllers, customizing them for their needs. And Google, as we mentioned, uses it for security in its Titan M2 chip found in Pixel phones and Chromebooks, besides the big Android push. These aren't small niche players. They're titans of the industry placing real bets.
Okay, so given this widespread adoption, where does RACV truly shine today? What are its current strategic application strongholds?
Well, its absolute dominance right now is still in embedded systems and IoT. That was its original beachhead, and it remains its most mature market.
Why is it such a good fit there?
It's that combination of simplicity, low power, small silicon footprint, and crucially, the royalty-free nature. It makes it a natural, almost default choice for many cost-sensitive and power-sensitive IoT devices. Designers can easily customize the microcontrollers with specific features they need, or even add those unique custom instructions we talked about for an edge in performance or efficiency. This market segment has already shipped the highest volume of RISC V cores by far and is projected to stay the largest for some time.
Okay, embedded in IoT makes sense. But you mentioned automotive, from tiny sensors to massive vehicles. The auto industry is undergoing this profound shift to software-defined vehicles, SDVs. How does RISC V fit into that complex picture?
Yeah, the shift to SDVs is enormous. It creates this massive demand for flexible, scalable, secure computing throughout the entire vehicle. And RISC V is rapidly emerging as the architecture of choice there. And it's not just for technical reasons, interestingly.
What else, then?
It's also seen as a strategic hedge against vendor lock-in and geopolitical supply chain risks, especially over the exceptionally long product life cycles. In automotive, 15, maybe 20 years for some platforms.
Yeah.
Companies don't want to be tied to a single proprietary supplier for that long if they can help it.
Right, that long-term view is critical in auto.
Absolutely. And the formation of that Quintoris joint venture, that's Bosch, Infineon, NXP, some real heavyweights specifically to accelerate RISC-V adoption in automotive, plus Infineon's own Kivit we discussed. Those are crystal clear indicators.
What are the technical advantages for cars?
Key advantages included scalability. You can use RISC-V cores from tiny sensors up to powerful central compute units. There's robust support now for functional safety standards like ISO 26262 up to the highest level, ASIL-D. And again, that customization allows automakers or Tier 1 suppliers to tailor chips for specific automotive workloads, like powertrain control, ADS, or infotainment.
It also sounds like RISC-V is becoming a really crucial underlying enabler for the whole AI revolution.
Absolutely, it's deeply connected. With Moore's law slowing, as we said, sustained performance gains for AI and machine learning have to come from specialized hardware, from accelerators.
Right.
But the field of AI is evolving so fast. Think about how quickly algorithms change, like the rise of the transformer model recently. Building fixed-function hardware for that is really risky. It might be obsolete quickly.
So you need flexibility.
Exactly. And this is where RISC-V provides the ideal flexible foundation. You get a stable standard control plane, the RISC-V core managing the accelerator, combined with the power to add custom extensions, like that incredible V extension for vector processing, or even completely custom instructions to accelerate novel computational patterns as they emerge. It's becoming the de facto standard for the control processors within complex AI accelerator chips, ensuring that flexibility for future AI innovations.
So it's like the smart manager for the specialized AI muscle.
That's a great way to think about it, yeah.
And is it expanding beyond these core areas embedded auto AI control?
Yes. It's definitely establishing emerging beachheads in other higher value markets as well.
Such as?
In data centers and high-performance computing, or HPC. This is often driven by the hyperscalers, the Googles, Metas, Alibabas, designing their own custom silicon tailored for their specific workloads. Alibaba, for instance, has been developing server-grade RISC-V CPUs.
Okay, data centers too. And consumer electronics.
Yep. It's appearing in wearables, as we noted with Qualcomm, smart home devices. And critically, with Google's official Android backing, that really paves the way for future RISC-V smartphones and potentially tablets or laptops down the line. That could be a huge market.
Let's turn to the geopolitical implications then, because RISC-V has undeniably become a pretty significant player in the global tech rivalry, hasn't it?
Indeed, it really has. China's aggressive adoption of RISC-V is probably the most prominent example. It's a direct and frankly strategic response to its perceived technological vulnerabilities and, of course, U.S. export controls, especially after the sanctions hit companies like Huawei hard.
So for Beijing, it's a path away from U.S. tech dependency.
Exactly. For Beijing, RISC-V is seen as a critical pathway towards technological autonomy and semiconductor self-sufficiency. And this isn't just talk. It's a clear top-down and bottom-up initiative. You have government policy guidance, massive state-directed investment. You hear figures like Alibaba planning tens of billions for AI and cloud infrastructure that prioritizes RISC-V, and major Chinese tech companies like Alibaba, Huawei, Tencent are all actively participating in RISC V International, the standards body.
This must present a fascinating, maybe difficult dilemma for U.S. policymakers, right? Should they try to restrict China's access or involvement, or should they embrace the open standard nature?
It's incredibly complex, yeah. There is definitely a contingent of U.S. policymakers and voices in Congress who view China's deep involvement as a direct threat. The core concern is that China could use RISC V to design advanced chips, maybe for military applications, thereby circumventing U.S. export controls on proprietary technologies like high-end ARM cores or EDA tools.
But can you even restrict an open standard?
That's the rub. Regulating a global open standard that's headquartered in neutral Switzerland is legally and practically very, very difficult. Trying to prohibit U.S. companies from collaborating within RISC V International would likely be counterproductive. It risks ceding leadership of this foundational standard entirely to China or others and could actually harm U.S. competitiveness in the long run.
And didn't you say the U.S. government itself uses RISC V?
Ironically, yes. The U.S. government, particularly through DARPA, the Defense Advanced Research Projects Agency, has been an early and significant adopter and funder of RISC V research, specifically for developing more secure military systems. So the picture is far from black and white. It's a real tightrope walk for policymakers.
So it seems it's not just a simple duality between the U.S. and China then. You mentioned RISC V becoming a kind of standard of neutrality.
Precisely. I think that's a really good way to frame it. RISC V's geopolitical significance extends way beyond just the U.S.-China rivalry. Other nations and blocs think Europe, India, they also view it as a critical tool for their own technological sovereignty. It reduces their dependence on proprietary technologies that come primarily from either the U.S., like Bi-86 or high-end ARM, or potentially from China in the future.
So it enables a more multipolar tech world?
Exactly. It positions RISC V as a strategic platform for that kind of world where no single nation or company holds exclusive control over the fundamental chip architecture that everything else is built on.
And how does all of this reshape the actual semiconductor supply chain, which, as we know, has traditionally been dominated by just a few very powerful players?
It fundamentally alters the dynamics. RISC V introduces this third, truly open path alongside the proprietary paths of x86 and ARM. This enables much greater diversification for chip buyers and designers. It reduces vendor lock-in, fosters a more resilient and competitive global supply chain, really, by lowering the barriers to entry for chip design. It democratizes innovation on a global scale. Companies anywhere can now potentially design competitive custom chips without massive upfront licensing costs.
Okay, so while the trajectory for RISC V looks incredibly promising, almost inevitable in some ways, every revolution faces challenges, right? What are the main roadblocks or hurdles that RISC V still needs to overcome on the road ahead?
Yeah, absolutely. No technology is perfect. Probably the most talked about challenge stems from RISC V's greatest strength, its extensibility and modularity. That strength is also its potential Achilles heel. The risk of fragmentation.
Fragmentation, meaning too many incompatible versions.
Exactly. If software compiled for one vendor's RISC V chip, maybe with some custom extensions, can't run properly on another vendor's chip that's supposedly implementing the same baseline standard, then the core value proposition of having a unified open standard starts to break down. It creates headaches for software developers.
That sounds like a serious risk. How is the community addressing that potential pitfall?
They're being very proactive about it, actually. The main mechanism is the development and promotion of RISC V profiles. Think of these as predefined, fixed combinations of a base ISA, like RV64GC, plus a specific set of standard extensions tailored for a particular application class.
So like a guaranteed minimum feature set.
Precisely. For example, there's the RVA23 profile, aimed at systems running operating systems like Linux or Android. This gives software developers a stable, guaranteed baseline they can target for portability. It ensures that core OS and application software will run across compliant hardware while still allowing vendors to add their own differentiating custom features on top or for specialized markets.
Does that solve it completely?
It helps significantly. And it's also worth remembering that the incumbent ISAs, despite their perceived maturity, also have their own forms of fragmentation. Different versions of ARM cores have different features. Bi-86 has countless instruction set extensions added over decades. So it's not a problem unique to RISC V, but one they are actively managing.
Okay, fragmentation is one challenge. Another must be verification, right? You said it's royalty-free, but the cost has to shift somewhere, doesn't it? Designing chips is expensive.
Exactly. The cost doesn't disappear. It often shifts internally towards the complex and very expensive process of design verification, or DV. The burden is really on the companies adopting RISC V, especially if they modify a core or add custom extensions, to rigorously ensure their implementation is bug-free and fully compliant with the standard. A bug in hardware is extremely costly to fix after manufacturing.
So how do they handle that verification burden?
Well, the ecosystem is actively rising to this challenge too. There are robust, open-source verification frameworks becoming available, like RISC V from Google and others, and formal verification methods using tools like RISC V Formal. RISC V International also provides architectural test suites to check compliance. And of course, the major commercial EDA vendors like Synopsys, Cadence, Siemens EDA offer sophisticated verification environments specifically for RISC V designs.
So it's a trade-off.
It really comes down to an economic calculus for each company. It's a strategic trade-off between paying external licensing fees and royalties to someone like ARM versus investing in the internal engineering effort required for rigorous integration, verification, and validation if you choose RISC V, especially for custom implementations.
Makes sense. Now, in this open world, how do you handle security? There's often this lingering concern about security by obscurity, the idea that if a design is secret, maybe it's inherently more secure because attackers don't know its details.
Yeah. That's a common argument, but it's largely seen as a fallacy by most security experts today. RISC V's primary security strength is actually argued to be its transparency.
How is transparency a strength for security?
Because the open ISA can be scrutinized by security researchers worldwide. Anyone can examine the specification for potential flaws or weaknesses. This makes it far less likely that hidden backdoors could be inserted by a single entity, and much more likely that unintentional vulnerabilities will be found and fixed by the community before they get widely deployed in silicon.
Has that actually happened? Found and fixed things?
Yes. There was a notable study by researchers at Princeton University back in 2017, for example. They analyzed the RISC V specification and did find some potential security issues and ambiguities, which were then discussed and fixed by the community precisely because the specification was open for review. That's harder to do with a closed proprietary IS.
But couldn't someone take an open source RISC V core design and add a hardware Trojan before manufacturing it?
That's certainly a risk with any hardware design, open or closed, especially concerning supply chain security. However, the argument is that the transparency of popular open source core designs at least makes it easier for others to audit the design for such malicious modifications compared to a black box proprietary core. But verification is still key.
So how is RISC V being actively secured beyond just being open? Are there specific security features?
Yes, absolutely. The ecosystem is developing a multi-layered security framework. We already talked about the privilege levels and the physical memory protection PMP unit for memory isolation. There are also dedicated security-focused ISA extensions being developed or ratified for things like faster cryptography, secure boot, and countermeasures against side channel attacks. And there are efforts to build full trusted execution environments, TEEs, on top of RISC V.
Any really advanced security work?
Yeah, there are also very advanced research projects like Cherry from Cambridge University and SRI, which aims to provide fine-grained hardware memory safety capabilities. And Cherry is being actively prototyped and implemented on RISC V, which could offer fundamental protection against entire classes of vulnerabilities like buffer overflows. Okay, interesting. And finally, let's circle back to the big one, ecosystem maturity. Can RISC V realistically catch up to the decades and billions of dollars invested in optimizing software and tools for ARM and by 86? They've had such a massive head start. It's true. Acknowledging that RISC V still lags behind in overall ecosystem maturity compared to those deeply entrenched players is important. The sheer volume of optimized libraries, specialized developer tools, and experienced engineers for ARM and by 86 is vast.
So it's still a gap.
It is still a gap, yes. However, what's often overlooked, I think, is the accelerated pace at which this gap is closing. It's not linear. Propelled by that huge collaborative effort in the RISE project, the increasing availability of affordable development hardware, and the successful porting of key software platforms like Linux, Android, and major real-time operating systems, the collective momentum is truly substantial.
So the slope of the curve is steep.
Very steep. It's like watching a high-performance race car rapidly closing in on a well-established but perhaps less agile competitor. The gap exists, but it's shrinking faster than many might have predicted even a few years ago.
So as we wrap up this deep dive, what's the inevitable future for this ISA? Where is RISC V ultimately heading? How will it fundamentally change the computing landscape?
I think RISC V is on a clear trajectory to become a fundamental, ubiquitous layer of the computing industry. Much like essential standards such as Ethernet or USB are today things we just take for granted as the standard way to connect things.
It's like plumbing.
In a way, yeah, the fundamental plumbing for processing. Its future dominance isn't necessarily about completely replacing incumbents like ARM or x86 everywhere overnight. That's unlikely in the near term. But it's poised to become the default go-to ISA for the new era of heterogeneous computing, especially with chiplets.
Chiplets. How does RISC V fit there?
Chiplets are these small, specialized dies that can be mixed and matched within a single processor package. RISC V is perfectly suited to act as the flexible, standard glue or control fabric that manages communication between these diverse, specialized dies. Imagine a package with a high-performance x86 or ARM CPU chiplet, a powerful GPU chiplet, maybe a dedicated AI accelerator chiplet, all potentially managed and orchestrated by one or more efficient RISC V cores using a standard interface.
Ah, so it becomes the common language for these different specialist chips to talk to each other.
Exactly. It becomes the control plane, the management layer in these complex, customized systems on package. That's a huge potential role.
And what's the likely impact of this rise on ARM specifically, given that their whole business model relies on those licensing fees and royalties you mentioned?
This shift will undoubtedly continue to force ARM to adapt its business model. The very existence of a viable, credible, royalty-free open alternative like RISC V puts direct and permanent competitive pressure on ARM's traditional IP licensing model.
So ARM has to react.
They have to. They will likely be forced to continue innovating rapidly, perhaps by adjusting their licensing terms, maybe lowering fees in some segments, or offering more integrated hardware-software platforms to compete on ease of use and faster time to market. They need to find new ways to add compelling value in a world where the core ISA itself can be obtained for free. It's ultimately a healthy competitive force for the entire industry, I think.
So, for you, the listener delving into this, the rise of RISC V really means a future where the chips powering our world are likely to be more open, definitely more customizable, and potentially more resilient to some of those geopolitical pressures we talked about. The knowledge you've gained today hopefully equips you to see beyond just the surface of technology and understand these deeper strategic forces shaping the very foundation of our digital lives. Which leaves us with a final thought for you to maybe mull over. What does this democratized approach to chip design, making it potentially easier for more people, more companies, more countries to design their own custom silicon, what does that mean for the next big technological breakthrough, the one that you might even be a part of?